today, I wanted to talk about battery and the role that batteries play in the energy transition, and I wanted to give you a perspective in terms of control, how the control field has been used, it can be used to really improve this technology and to really make an impact. And so within that, I would also like to share some of my journey. So one question that I get asked a lot is, how do I get in this field? So let me just start with this infographic, and this is, the state of the art. This infographic tracks the state of electrification in the United States by sector. And as you can see, the industrial and the transportation sector have the highest potential for electrification. And so if with the transportation having the majority of this potential, with 99.8% of the energy used not being electric. So electrification is indeed a crucial building block for the economic-wide decarbonization, but we don't really do much unless we find a reliable, effective way to store that energy. And so energy storage plays indeed an important role in this transition. And if you think about it, you really don't do anything with an electric vehicle if you need to keep the vehicle plugged all the time, right? So we need to find ways to store that energy. And so when we think about energy storage technologies, electrochemical energy storage technologies like batteries, lithium-ion batteries, really make sense. Why? Well, because we don't pay a penalty dictated by the second law of thermodynamics. So we look at batteries, a really valuable solution, a valuable way to help electrify the transportation sector as well as other sectors. And so in today's talk, I would like to really share with you a couple of key ideas. The first one is that system-level understanding is really essential for identifying valuable pathways for scaling, and also how collaborating with key partners such as industry can help uncover effective strategies for deployment and impact. And these two key ideas are really drawn by my own experience over the past 15, 20 years. So, but before I dive into this, I really wanted to share some of my journey. My journey started in a small town near Rome, and this is a very old town, so I grew up surrounded by the ancient ruins, and since I was a young girl, I wanted to become an archaeologist. I was fascinated by those ruins. I wanted to uncover all, those secrets. Why do we still see those beautiful pieces of art today? And what was done at that time. Now, it's true that the field of archaeology wasn't exactly booming at that time, and then as I also got more and more interested in this field, I also got to know that, as we all know, ancient Greek and Romans were wonderful engineers. And so they pioneered the philosophy and art, but they also are responsible for incredible things like, innovation in construction and water systems and also military tech. And so I pivoted, like, okay, well, if I cannot be an archaeologist, at least I'm trying to be an engineer. And so when I started college, I wasn't really sure what type of field I wanted to get into. And at that time, I was also started looking and to be interested in Formula One racing, and I just enjoy watching the race. And what you also learn if you are in this field, in these things, and if you ever watch one of those races, is that well, the driver counts, but it's the pit crew that really makes a difference. We're talking about fraction of seconds, and there is so much synchronization and optimization that goes into really make that team performing, in a way that you can really eventually win the race. So I started asking myself, what do I need to know to be able to develop skills that will allow me one day to apply for a job in this field? And so it was clear that control system, control theory was at the heart of this work as I learned later. Now, I didn't know what control system engineering was, and I feel compelled today to really bring a definition of this field. So control engineering is a field of electrical engineering, and it's a discipline that applies lots of math into the design of systems with predictable behavior. So what you have there, you have a dynamical system that vary over time, so you have sensing and actuations, and you use feedback, which is the core concept of control system, to infer and to make a decision as to how to design a control strategy to steer your system where you want it to go in face of uncertainties and disturbances. And so feedback control is everywhere in nature and in our body, our temperature control system, and how we control our system, control our glucose in our blood, and also it's everywhere in devices that we build. So from autonomous vehicles to batteries, for example, and satellite. And so I spent all my college years, master and PhD, looking into all these beautiful set of mathematical theories from estimation theory, optimization, optimal control. And as I was wrapping up my PhD, I felt that the real potential for control, the real impact of these methodologies was not just in the theory itself, but was in the application of them. And so I shift gear, and I started working and looking at how and where can I apply this knowledge. And so my journey in sustainability started almost 15 years ago when I was starting my postdoctoral job at Ohio State University. And at that time, there was a big need to understand how to optimize hybrid electric vehicles. So hybrid electric vehicles are this, advanced powertrain system. And what they have two actuators. They have a gasoline engine, and they also have an electric motor and a battery. And so at each instant of time, you have to make a decision as to which actuator to use to minimize the fuel when the vehicle goes from A to B. And so this really opened up all sorts of new developments. And so you can frame this an optimization problem. You can create models, and those models can be as detailed as you want them to be. And also, you can apply and develop different optimization methods. But what's the key here? So the key for me was to really make sure that those algorithms were deployable. I didn't just want to create nice theory around this powertrain, but I really want to make sure that those algorithms could be used in real vehicles. So it was very important to have collaborators, industry collaborators at the time, that could really give me feedback as to what constraints I was working with if I were to deploy my software in a real ECU, and also what type of performance were required and things of that sort. So I was really, very excited about this work. We collected our algorithms with my collaborators in this monogram that has been published by Springer. And so I saw an opportunity there to really push this even further. So when I joined Stanford University 7 years ago, I founded the Stanford Energy Control Lab. And so how to apply, basically the idea here is to use and apply and leverage those theories to the aim of advancing the energy transition and to really make an impact in this area. And so I had the pleasure to work with wonderful students and great collaborators, and we really dug into many details of battery control, as Scott was mentioning earlier. And so we spent the first few years of my when I joined Stanford in developing a nice pipeline for battery management system, and I brought today some samples, some cells. So think about, those are lithium-ion battery cells. They're very small. Those are cylindrical types, and those cylindrical cells are connected together electrically and also thermally to form a pack of modules, and you have many of these modules to create a pack that goes in a car or in an electric bus. So this is a pack of an e-bike. And so there are, so the development that we went through was consisting basically in creating models for single battery cells, creating, understanding of the electrical, electrochemical, aging, and thermal dynamics, and also looking at how these cells could be connected together and what it means, for example, to define and design optimal charging strategy of the pack, for example, as opposed to single cell. So, we developed this beautiful, in my mind, pipeline on battery management system design. But what was the catch? So what was the problem here is that we were kind of forgetting something very important, that when we use those batteries, we use them in a very specific application, whether it's an electric vehicle, so grid storage, or an electric vacuum, or a laptop. And so depending on the usage, the battery will undergo very different degradation trajectory. And if you're trying to define and create estimation algorithm for health and degradation, you really need to account for this. You need to know the application, because otherwise you're going to just working in the dark. And so that's the feedback, right? So we cannot just deploy algorithms when we do them in the lab. We need to make sure that we know what's going on when the system is operating. And also another element that we weren't really accounting for was that our development was done in the lab and validated in the lab. And we all know that there is a disconnect between laboratory testing and real-world usage. And so we've been spending the past few years, 4 years, to kind of address and really make sure that those elements were being, investigated and addressed. And so I want to go over some examples of 3 works that we've been working on. And the first one is this work with Professor Chu and his lab, leveraging the experimental facility at SLAC, the Stanford SLAC Battery Center. And in this work, we've been trying to bridge laboratory testing and real usage. This is a spoiler alert. The paper is under embargo now and is going to be published on Monday. But what we've been doing in this work was to ask a very simple question. How is dynamic cycling affect life? And how does that compare with life that you predict and you can achieve when you do very simple charge and discharge testing? And this is something that everybody kind of know that there is a disconnect, but no one has ever quantified that. And so probably we are the first who come up with some quantitative measure of how much real driving really can improve life. And under certain operations, we can get up to 40% of additional life from these batteries when they operate via dynamic cycling. And what that number means, if you translate them in additional miles that you can get of the vehicles, you are talking about around 100,000, 110,000 miles more. And so we've been doing this, and we also came up with so many other takeaways from this work, one of which, for example, is we understood how not only when the battery fails, but what are the mode of operations that lead to the battery to fail. And this is very important because in this way we can also now build more accurate aging models that we can put in our battery management system, as opposed to making an assumption that the aging operation is detected by, for example, solid electrolyte interface at the anode. This second example is related to learning from real operation. We've been working with our industry sponsor, VW, over the past 4 years. And within this collaboration, we get the chance to get field data from the CAN bus of a battery pack. And we had the chance to create technology that will integrate basically real-world driving into the battery management system software. And what that does to the battery is to make it more resilient and last longer. And there is also lots of learning that we get from this type of work, which is, for example, we now know that the battery sits most of the time doing nothing, and that leads to calendar aging that we don't really tackle in laboratory efforts. And last example I wanted to share with you today is this work we are doing with Oak Ridge National Lab through a Department of Energy project in Ohio State. And my student Joseph is leading this effort. Joseph is a fourth-year PhD student in chemistry. And this work stems from the observation that despite being just a few, the heavy-duty commercial vehicles are responsible for quite a bit of CO2 emissions. And we're trying to understand whether or not it makes sense to electrify these vehicles in application like first mile or drayage application. So basically, you are at the port, a seaport, and you use those vehicles to move, goods from the ports to warehouse. And this is a region of 50 to 250 miles radius, and it's a distance that is good enough for lithium-ion battery technology to really be used for the electrification. And so we're building all those models and the suite that will help us to understand, for example, how battery size ensures the maximum coverage of routes. We have different routes. We're looking at the port of Savannah in Georgia, and how does deploying renewable energy and energy storage change the total cost of ownership for an electric truck, and other questions of this type. And at the end of the day, we go to a fleet operator and present what are the viable roadmap for electrification of the fleet. And so, in conclusion, I wanted to make just a couple of remarks here. I wanted to, from my experience, really what's been very important is to really work collectively with the faculty, in this case, faculty of the school, faculty across the school, across the university, and also with our national lab, because this really takes a village to drive meaningful change. And in addition, a system-level perspective can really be, it's what, in my experience, has helped me to guide technology development, understand what are valuable paths for scaling and for impact. And lastly, one thing I'm very excited about is that I will be on sabbatical next year, and so that really, it's something that I would love to, happy to share. And with that, I'm happy to take any questions you might have. Thank you.